Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving headfirst into the fascinating world of homomorphic encryption, specifically Apple's implementation in iOS 18. Get ready for some seriously geeky goodness.
Ooh, homomorphic encryption. Sounds intense. I'm all ears, or rather, all speakers. What's the big picture here? Why is Apple using this?
Basically, Apple wants magical image search in photos, right? Find all your dog pictures instantly. But they also want to keep your data private. The classic dilemma.
Right, the privacy versus functionality tug of war. So how does homomorphic encryption solve this?
It's like magic. They create these embedding vectors, numerical representations of image concepts. Think of it as a super high-dimensional space, where each dimension measures something like dog-likeness or wild-likeness.
So a wolf would be high on both axes? I see. But how does encryption fit in?
Exactly. Normally, sending these vectors to Apple's servers for comparison would be a privacy nightmare. But with homomorphic encryption, the vectors are encrypted before they're sent. The server can perform calculations on the encrypted data, like finding the closest matches, without ever seeing the actual data.
That's mind-blowing. But how does that even work? I mean, how can you do math on something you can't see?
That's the beauty of it. It's all about special mathematical operations. Think of homomorphic addition. EP plus EQ equals EP plus Q. You add two encrypted values, and the result is the encryption of their sum. Same with multiplication. The server can perform these operations blindly, without knowing the underlying values.
So the server does the heavy lifting but stays completely in the dark about the actual content? Amazing! But there are limitations, right? It's not perfect magic.
You're spot on. It's not fully homomorphic encryption. That would be ideal, but it's too slow. Apple uses somewhat homomorphic encryption, which has limitations on the number of operations you can perform before the encryption breaks down. Think of it as a noise budget. Each operation adds noise, and eventually, the noise overwhelms the signal.
So it's a trade-off between privacy and performance. Clever. What about other privacy concerns? The article mentions other leaks besides the embedding vector itself, right?
Absolutely. They also address leaks related to which cluster the query falls into and the metadata retrieval. To mitigate these, they use techniques like differential privacy and a clever anonymization network. They even send fake queries to throw off potential attackers.
So it's a layered approach to privacy. Impressive. But the author mentions some skepticism, particularly about the anonymization network. Is that a valid concern?
Yes. The author points out that even with the anonymization network, there's still a theoretical risk of collusion between the parties involved. It's a valid point, highlighting the inherent complexities of achieving perfect privacy in a distributed system. It's not a flaw in the homomorphic encryption itself, but rather a limitation of the overall system design.
So the system isn't foolproof, but it's a significant step forward. It's a fascinating blend of cryptography and practical engineering trade-offs.
Precisely. It's a testament to Apple's commitment to privacy, even if it's not perfect, and the whole thing is just incredibly cool from a technical standpoint. It's a glimpse into the future of privacy-preserving computation. It's pretty exciting stuff.
Definitely. Thanks for breaking this down. I feel much more informed now. It's a complex topic, but you made it surprisingly accessible.
My pleasure. And that's all the time we have for today's Tech Bytes and News. Thanks for listening, and we'll catch you next time. Goodbye.
Bye-bye.